This will be the last foundation seminar for this semester, and it's a pleasure to have our own Evita Verheijden telling us about cryptographic censorship. Evita, it's all yours.
I guess this is the first time I'm here in this presenting in this room, so now I understand the struggle of figuring out where to be. But I'm sure it will work out.
It's encrypted.
What is the complexity class? Yeah. Good. So today I'll be talking about cryptographic censorship, which is a paper that I put out 2 months ago with Nada, who's a PI here. Osman, her student at former student, I should say, because he graduated last week. At MIT, Adam, who's a postdoc there, and Lisa, who is also another student. And we called this work cryptographic censorship, and I think I briefly talked about this at the last meeting, because we're using tools from computer science, and in particular from cryptography, to sort of gain traction on the problem of weak cosmic censorship. So I want to start.
You have to click on the.
Okay, by reminding you of the problem of weak cosmic censorship. So in general relativity, the evolution of smooth initial data generically results in curvature singularities. And there's this expectation that the formation of the event horizon is likewise generic. And this is a statement of weak cosmic censorship that singularities resulting from initial data evolution should generically be hidden behind horizons in gravitational collapse situations. Now, this idea is kind of ubiquitous in a lot of the work that we do. So maybe let's talk about why should we care about cosmic censorship. So first, in classical GR, we kind of care about it just because we like it. So it's nice that cosmic censorship provides for us that GR is deterministic outside of horizons, and then also there is this kind of lack of observed naked singularities. So this principle would help to explain why we don't see any naked singularities in the sky, as far as we know. But nothing kind of catastrophically breaks down if we don't have weak cosmic censorship in the theory of GR. However, I want to argue that in quantum gravity, we should care about cosmic censorship because we need it. And I want to give 2 reasons. The first is bulk reconstruction. So this is, I'll talk about this a bit later. But this is this thing that we do in holographic theories of quantum gravity, where we try to understand observables in the bulk of our spacetime in terms of some dual description. And in bulk reconstruction, many of the results rely on the assumption of global hyperbolicity. And global hyperbolicity implies weak cosmic censorship. So if we lose weak cosmic censorship, we would lose many results in bulk reconstruction. And the second point is the statistical interpretation of black holes. And this is very sharp in theories like ADS-CFT, but it does predate it. It's more general than that.
Sorry.
Yeah, go ahead.
Take it to unmuted.
I am unmuted. Should I?
I'll get back to you. Yes. We are saying, okay, it's immediately. Helen is coming.
Oh, okay, cool.
Sorry.
No, you're good. Yeah, so the statistical interpretation of black holes, where we think of this is working. Yeah, where we think of black holes as thermal or thermalizing systems with some interpretation in terms of the microstates of some thermodynamic ensemble. For example, we have equilibration of the event horizon, which then corresponds in ADS-CFT to the sort of thermalization of the OTOC, where things like scrambling, chaos in the CFT. And all of these notions kind of work out if typical states have event horizons. If typical states would have naked singularities instead, it would be kind of a miracle or a conspiracy that these results in black hole physics so well reproduced by results in
Is that
CFT
saying
dynamics.
that the information loss paradox is unresolvable if you have no horizon? I mean, there's nowhere to store the information.
I guess that's one way to think of it. I want to say that maybe the black holes that we think of in the black hole information problem, if we think about like fast collapse, those are not actually typical states in the sense that I'm talking about. But it's true that especially in like the ADS CFT resolution of the information problem, that does rely on certain notions like this. Yeah.
Sorry, just a totally uninitiated question.
Mhm.
So is the idea that there is some ensemble of states and most of them have event horizons, but not necessarily all?
That's right. That is part of what I will advocate for.
Okay.
So the notion of typicality is just a mathematical notion
Sure.
of
Okay.
states that are close to the average. And this is not. So I'm going to advocate for the idea that typical states should have horizons, which is different from saying that generically,
I see.
which is a statement about like, open subsets of solutions to the
Sure.
arguments equations. Yeah. But I guess what I want to say is that in quantum gravity, we need at least some version of weak cosmic censorship to explain these results in theories of quantum gravity that we have some control over. All right, so you might say it's probably true, right? There's all these good reasons for it to be true, but actually it's most likely false in its current formulation. So not only is there no proof of the weak cosmic censorship, so this annoying mathematician could be like, well, we don't know that it's true, but it's actually not true in the sense that there's many counterexamples. So let me start with this kind of concrete one where we have these authors and in various subsets of them have constructed large sets of initial data on asymptotic ADS4 with various matter profiles that result if you evolve them into naked singularities. But many of these examples,
Are they generic examples or do
Yes.
they assume symmetries?
no, they're generic. Well,
They're spherically symmetric or equivalent.
that's right, but they're generic in the sense that if you perturb the initial data, it will still result into naked singularities. So
But
they-
beyond symmetries,
I think they.
they must
Yeah.
have symmetries,
Yeah.
right? So that has always been the argument, because there are counterexamples in 3+1 gravity. But these have all been ruled out saying, but this is spherically symmetric. So why is this?
ruled out in the sense that,
People say don't need to take it seriously because it's not generic.
but sorry, I think there's two notions of genericity. The notion of genericity that people care about for weak cosmic censorship, the formal statement, is the sense that if you start with initial data and you perturb the initial data, you will still get a naked singularity.
Yeah,
That's the
only
notion of
question is-
genericity.
Sure, but perturb within the symmetry group or perturb completely generic? That's the question.
Well, these will still be asymptotic ADS solutions. If that's
Are
what
they
you're asking.
spherically symmetric?
Yeah, that's the question.
I would have to look it up. I don't know.
Yeah, but
Well, it's numerics. Yeah.
But at least the paper I know from from G16, they do numerics with just one radial direction. On break and there's ABS4, so you need to not break this.
That's right.
This.
Yeah.
The other paper, I don't know. The Chrisford and
There is a whole series of papers that they consider.
There are also analytic solutions with just Dustin spherical symmetry and asymptotic blackness. Like the sense of genericity.
Yeah.
They value cosmic.
yeah, that's what I was.
Yeah.
That's the solutions exist. You know,
Yeah. So there's serious violations.
Yeah.
well, this is where the dispute comes. People say, it's not serious, spherically symmetric, come on.
and possibility.
Well, yeah.
This is absolutely.
Yeah. Obviously, this is a theory talk. And for the notions of weak cosmic censorship that we would require in to have a consistent theory of quantum gravity, it appears that this is a serious violation. Maybe let me say the following thing, which is interesting about these examples, is that many of these examples also violate what's known as the weak gravity conjecture, which is a conjecture that consistent theories of quantum gravity should obey. And if you tune these matter profiles in such a way that you restore the weak gravity conjecture, they actually go away, these naked singularities. So that has been taken as some suggestion that I'm really struggling with this. That maybe naked singularities cannot exist in classical. That violations of weak cosmic censorship can happen in classical GR, but that once you look at consistent UV complete theories of quantum gravity, it cannot be violated. So that there's some sort of swampland censorship. However, there's other counterexamples, really old ones to weak cosmic censorship, like Garvey-Laflamme instabilities, which happen in higher dimensions when you have black strings that can pinch off and they form naked singularity. And then if we include quantum effects, we can also have black hole separation.
It's a string theory result.
No, it's classical.
It's classical, so you
Yeah.
have a black hole. In pure
It's like
general
yeah,
relativity,
it's just extended objects.
that is a black string, so because it's a Schwarzschild black hole with an efficiency of 5 dimensions, so it's like this cylinder. Event horizon, it's pure general relativity vacuum 5 dimensions solution.
And it collapses too.
It's unstable, and so it kind of has these sort of movements like this. I don't know what the formal description is, but and what happens is kind of with like strings of fluids. It happens also in just fluid dynamics. Is they can pinch off, and that moment of the pinch off is very singular. So those are naked singularities, and the expectation is kind of that very quickly it restores to a description or to a situation that is non-singular. But that pinch off point is naked singularity. Right, and then so with quantum effects, we have black hole evaporation, and the endpoint of that also violates weak cosmic censorship. But similar to what I was just saying about these singularities, naked singularities in Garvey-Laflamme being kind of short-lived in a way, there is some sense in which these types of singularities are kind of small. So they're tiny violations of weak cosmic censorship, even though they might be generic. And so there's some intuitive sense in which this naked part of the singularity is small. And so the goal of this work was to make precise what we mean by small and work towards this quantum gravity version of cosmic censorship that might rule out large classical violations, but allows really small quantum gravity violations. So that's what we do in this paper. We obtain a proven condition, a general condition for the formation of event horizons that applies in broad generality. That's what we call cryptographic censorship. And then secondly, we have it if we classify singularities, and in particular naked singularities, into different sizes and classification of how severe they are. And then to obtain a true formulation of quantum cosmic censorship, we need some precise relation between these first 2 points. We don't have that, but we have some conjectures relating the two. And all of this talk will be in the context of ADS CFT. The reason being that that's where we have the tools that we need to prove this cryptographic censorship statement, because we'll be using the quantum description on the boundary. But the expectation is that we can learn some more general lessons about theories of quantum gravity.
So does this mean that naked singularities, there's a dual description on the boundary as well, or?
Actually, that's a very good question. So I was going to say no, but actually today, or I guess in American time, yesterday night, there was a paper on the archive that is obtaining kind of that by Honglu and collaborators in Honglu at MIT, and then a group of friends at Cambridge, Oxford. I forgot. Sorry, I just saw this like a minute ago. So it's exciting, but there seems to be some dispersion. All right, so what I want to do in the remainder of this talk is I want to kind of briefly go over these first 2 points, and then in the remainder of the talk, I'll elaborate on them. But first, I want to give some background for the context that we're working in. So this is ADS CFT, so many of you have seen some version of this slides a million times probably. But just to recap, so this is the suggestion that quantum gravity and anticonsider is dual to a lower dimensional non-gravitational quantum field theory, which is really an equivalent description of the same physics. And then oftentimes people like to say that this non-gravitational description lives on the boundary of ADS, and that's a very nice way of thinking about it, but it's really just two equivalent descriptions. And then there's a dictionary relating these two, which we colloquially refer to as the bulk and the boundary. And then the regime that I'll be interested in and that many people work in is small G Newton times H blank, which corresponds in the bulk theory to an approximately semi-classical theory of gravity, which is Einstein gravity. All right. And then this tool that I'll be using is called bulk reconstruction complexity. I already referred to it briefly. So bulk reconstruction is the question of how to represent bulk operators that might appear in the boundary description in terms of expectation values of some operator in the CFT. And there is this notion or this idea that bulk reconstruction in the causal wedge, if you look at the entire boundary, you just look at whatever is causally accessible to the boundary observer, that reconstructing the interior of the causal wedge is a simple task, meaning that it's obtainable basically by semi-classical observers, or that is polynomially complex in the boundary theory. So in this drawing, if we just have the cylinder, there's no black holes or anything inside the spacetime, then the causal wedge of the entire boundary is the entire space.
So Q in the bulk is local,
That's right. In the case of causal wedge reconstruction, we think of local operators
and
that are simple to reconstruct.
and then the expectation value on the boundary is calculated over what region? Is it over the whole boundary?
That's right.
So it's not local.
Well, you could look at on like a time band and do the reconstruction there, and then you can evolve in time. Usually you look at moments of certainty. But it's true that the ADS-CFT dictionary is a non-local statement. Okay, so the first thing that we obtain is this diagnostic of event horizon information. And I want to kind of intuitively motivate this idea from the point of view of bulk reconstruction. So like I said, reconstructing operators in the causal wedge is a simple task in the boundary theory. So what would it mean if we have an event horizon? It basically means that there is some boundary to that region. So that's how we like to think, or that's how we're going to define the event horizon. It's the boundary of the causal wedge. So that means that if there is something that is hard to reconstruct, that must lie outside of the causal wedge, and therefore there has to be an event horizon. So that's kind of the diagnostic that we're going to use if there is some operator that is non-simple to reconstruct. So technically what we're going to do is we're going to view bulk reconstruction as a learning algorithm, and then we prove that when the boundary time evolution is sufficiently pseudo-random, and I'll talk about what that means momentarily, then there always exists some operator Q such that its expectation value cannot be computed by this algorithm. Whereas this algorithm is capable of computing all of the expectation values of operators in the causal wedge. So that means that this operator Q needs to lie outside of the causal wedge. Therefore, the causal wedge is not the entire spacetime, meaning that there needs to be an event horizon. That's what we'll call cryptographic censorship. That pseudo-random dynamics guarantee event horizon information in typical states. And I'll discuss what this means, but the interesting thing is that for small g, which is the regime that we're interested in, is nearly all of the states. Okay.
So this is a statement that in the boundary theory, if you compute something to show that something is pseudo-random, that ensures for you that in the bulk there is something.
That's right. So one of the reasons, and if we get there, I'll say this at the end, that this is interesting is that usually to diagnose the existence of an event horizon, you need to evolve for the entire history of the spacetime. In this case, you don't. All right, so the second thing that we obtain is this classification of singularities. So let's think about what we do not want. So what we don't like to be allowed is singularities that are classically extended and that emit kind of large amounts of observable causally propagating radiation that is visible to asymptotic observers. And so we're going to formalize this with the definition of a classical naked singularity, where we talk about the size of naked, in particular, time-like singularities in terms of boundary data, which is a new tool that we introduce as a separate result in this work. Okay, so here's the plan. I'm going to talk about pseudo-randomness and complexity of learning, which is the tools that we need for this result. And I'll talk about cryptographic censorship, which is the main theorem in this work. Then I'll connect back to singularities and try to connect these two separate results into a statement about cosmic censorship. But before we're going to do all of that, I want to do kind of a warm-up exercise where we first see a connection between reconstruction complexity and event horizon information. All right. So we're going to prove that quantum extremal surfaces must lie behind horizons. So in many instances, the large curvatures that we usually associate to singularities, they also create what's known as trapped or extremal surfaces. And we're going to prove that the quantum version of these surfaces, quantum extremal surfaces, generically lie behind horizons. This is an extension of a result that Nana and Osman had some years ago, where they did this for the classical case, and here we include quantum effects. So the main tool that we use is what's known as a strong Python/Lange proposal. Yeah, I'm sorry about that.
This is the Python.
Yeah, this is the Python. You know, we are funny people in the end. No, weird. So this proposal distinguishes region of efficient versus exponentially complex reconstruction. So I already talked about this idea that the causal wedge is efficient to reconstruct, and efficient here means it's always a statement about how many steps or how much time you need in terms of the log of the dimension of the code subspace that you care about, which is basically kind of a subset of your Hilbert space that you're interested in doing this bulk reconstruction on. So that can be like a black hole plus some like matter around it. And the fluctuations of that matter would be the different states in recursive. All right, so the causal wedge is simple to reconstruct, and then the Python/Lange proposal states that the complementary region, which is known as the Python/Lange, is exponentially hard to reconstruct. And the reason that it's called the Python/Lange is because if you look at some time slice, then this is what the geometry would look like, and it's kind of like a Python that had too much to eat. Okay, so that's the idea of the strong Python/Lange proposal. Has not been proven, but there's a lot of compelling evidence for
Can you
it.
say something on how a quantum extremal surface differs from a parent horizon?
Right. So quantum extremal surface, like the apparent horizon is like is foliated by trapped surfaces, right? So it's a different codimension. But quantum extremal surfaces, they're basically trapped surfaces that are also extremal, but then they solve the quantum problem. So trapped surfaces would be, or extremal surfaces would be surfaces that both the inwards and outwards null expansions are negative. And in this case, that solves the same problem, but for the area plus the von Neumann entropy inside the region, or in the region bounded between the surface and the bound.
All right, can you just remind me, in what sense are they extremal? What bound are they saturating?
They're extremal in the sense that they're you cannot, if you move away from it, you will still land back on that extremal surface.
I see.
So it's just it's like a minimal or maximal surface.
I see.
Okay.
Yeah. So it's either a minimal or right. So I wanted to say that I'm going to assume this strong Python/Lange proposal here and on the next slide, but not in the remainder of this. Okay, so here's the informal proof. So acting on the Lange by the Python/Lange proposal is an exponentially hard task in the boundary theory. However, if any such quantum extremal surface lies in causal contact of the boundary, it would actually be very simple to act on anything that lies behind it, because one could just jump in, do some measurement here, and then go back to the boundary. But that's an immediate contradiction, and therefore quantum extremal surfaces must lie behind the horizon. Now, the actual proof is a bit more involved, but this is kind of the intuitive idea. So what I want to say is that this is the first way how you can connect reconstruction complexity, regions of efficient and exponentially complex reconstruction. I can relate that to the existence of horizons in your space. Okay. So what's all this talk about pseudorandom? So pseudorandom states and unitaries, there are states and unitaries that look like random states or unitaries, but contrary to random states and unitaries, which are not efficient to implement, these unitaries would be efficient to generate. So what do we mean by look like? Is no efficient quantum algorithm could distinguish a draw from a pseudo-random ensemble from a random draw. So what you should have in mind is there is some Hilbert space of all of the states in your CFT or equivalently to bulk geometries that you might care about. The code subspace is what we consider to be kind of the interesting states for the problem at hand. So for example, that could be a black hole with some matter around it, some fluctuations around it. So that would be our code subspace. And then the question is, if you make a random draw from that set of states, that would be a random state. But doing that, making that random draw is not an efficient process. That's kind of a mathematical statement. The more serious problem maybe that's more intuitive to think about is when you think about unitaries. So think of all of the unitaries that can be defined in your Hilbert space. Then making a random draw from that will give you some arbitrarily complex unitary that's just really hard to implement. So a pseudo-random ensemble, on the other hand, is some subset of all of these unitaries that if you make a draw, no one could tell you that you didn't draw it from using the random measure, but it is efficient to implement. So it seems to be very, very complex, but actually you can just go ahead and evolve it as the Hamiltonian of your system. Great. Okay, so that's kind of the intuitive definition of pseudo-random states and unitaries. And the reason that we might care about pseudo-randomness is that, well, I think I should have a slide about that. Yeah, so that's right. So we'll be working with pseudo-random unitary states. The reason is that we're going to assume that the CFT dynamics, so the boundary time evolution, is going to source chaos. And that's something that we often do in ADS CFT when we think about black hole spacetimes, because we have kind of, like I said previously, the thermalization or scrambling of the horizon translates into a statement about chaos in the boundary theory. So we're going to assume that the CFT dynamic sources chaos, but we're not going to assume that that chaos then again sources horizons, because that would be kind of tantamount to assuming cosmic censorship. So we just want to assume chaos and see how far we get from there. Now, these chaotic dynamics are often usefully and really successfully modeled with power random unitaries, or if you know about them with K-designs, which is a separate notion that we don't need to talk about. And these power random unitaries have been really, you can really see that they reproduce this chaotic behavior in the CFT. However, like I said, they're not efficient to implement, and we do kind of think that time evolution in the universe also works on short time scales. So a more physical notion to consider from that point of view is this concept of pseudo-randomness, because it allows for efficient generation.
So you start by, you say the world has chaos in it and CFT is its source. What is the argument of that first bullet point?
The argument is that in spacetimes with high curvatures, which usually also have horizons, we see that in the CFT description of such spacetimes, there is chaos. And often it's really highly chaotic. So the question is, can we kind of unentangle that chaos from the existence of horizons? Or is it the case that the moment you have chaotic dynamics, you also need to have horizons? And we're going to see that that's the case. Good, so to be precise, we will only need to assume that the CFT unitary, so the time evolution on the boundary, is well approximated by a pseudo, this is going to denote pseudo-random unitary, on our choice of code subspace. So again, kind of like code subspaces are the set of states that we care about for the problem at hand. So for any state in our code subspace, we want that acting with the unitary, the true time evolution on that state is almost the same as acting with some pseudo-random unitary, up to exponentially suppressed errors. Okay, so I needed to learn a lot of computer science to work on this project, and I thought it was really fun to learn. So I'm going to just talk about it because I think it's cool. So I'm going to give some formal definitions, but we'll walk through them, and if they're unclear, please let me know. So this is a formal definition of pseudo-random unitary. Pseudo-random unitary, so they come in some ensemble of some subset of all of the unitaries defined under Hilbert space. They're labeled by what's known in cryptography as a key, which is some random classical bit stream that you draw from what's known as the key space. And the idea is that both the Hilbert space as well as this key space are parameterized or they're like the dimension of their Hilbert space is proportional or parameterized in some way by what's known as a security parameter. And that parameter basically just gives you kind of this how secure your system is. So the idea is that you have some small randomness, some small classical randomness that now you're going to transfer to some set of unitaries such that they appear random, but really they aren't. So in this key, you draw some key that gives you some unitary. And then this ensemble of unitaries is a pseudo-random unitary ensemble if all of these unitaries are efficiently generatable. So that means that you can just implement them in terms of a quantum circuit in some limited number of gates or operations. That's the meaning of efficient. But no efficient quantum algorithm could distinguish a draw. This is what I mean by drawing some unitary from this ensemble from drawing unitary from the higher random ensemble, which I'll denote by mu. And then there's a similar definition for pseudo-random states. Okay, so again, the idea is you have some small classical randomness that you're transferring to this set of unitaries such that they appear random, but they aren't. Okay, now what is the type of reasoning that we want to use? It's going to go like this. We're going to consider some efficient quantum algorithm that has oracle access to the unitary. I'm going to say what that means right now. So we're going to denote that in this way. So what does it mean to have oracle access? It basically means that this algorithm, it can prepare polynomially complex states phi. And then it can give those states to the real time evolution of the system, the oracle. And then it gets back the time evolved states. And in that way, it's going to try and learn what that time evolution was, but it doesn't know what it is. It just feeds its state, it queries its oracle on what is the time evolution of this state. Now, what is the time evolution of that state? And then it's going to try and learn the dynamics. Okay. Now, at the end of that phase, it's going to output its best guess you had. So it's like, okay, this is what I think the time evolution is. And then it's handed the actual state psi of the system that you have, and it's asked to predict the time evolution of that state. And then the question is, how well does it do? Now, Neda and Lisa, a couple of years ago, I guess 2 or so, they proved that if the time evolution is pseudo-random or random, then this quantum algorithm, any quantum algorithm, is going to do a really bad job. So that's formalized in this theorem, hardness of learning pseudo-random unitaries. So if we consider some pseudo-random unitary ensemble, and also a pseudo-random state ensemble in some Hilbert space parameterized by this security parameter, then for any family of computationally bounded quantum algorithms that have oracle access to U, that then tries to learn the time evolution U and then produces its best guess U hat, then given the actual state, the system outputs its best guess for the time evolution, then they proved that on average, averaging over all the unitaries and states in your ensemble, then the fidelity, or basically the overlap between the real time evolution and the predicted time evolution, is bounded below 1 by a constant, which means that the overlap is small, so the prediction is bad. Okay. And then in particular, that immediately implies that there exists with high probability
So this overlap is at a given instant or the entire history,
it's at a given time.
given time.
That's right. But you could then evolve it and it will not get better.
Of course not, yeah,
Yeah.
right.
And then there exists with high probability some observable Q whose expectation value cannot be predicted by the algorithm. And that's what we're looking. Okay. Now, if we want to apply this theorem in like situations that we care about, like gravity, and in this case in holography, then what do we need? So we're going to assume, like I said, that the time evolution of the CFT in this case is well approximated by a pseudo-random unitary. Now, what do we need to apply this theorem? Well, first we need some notion of gravitational pseudo-randomness that is enough to source the chaos that we care about in highly gravitating systems to get scrambling, etc. And to obtain that, the only thing we need to do is choose this parameter that the dimension of our Hilbert space scales with. That we need it to be polynomial in n, and n is the degrees of freedom of CFT. Alternatively, this means that the dimension of the code set, the log of the dimension of the code set space is polynomial in n, or polynomial in 1 over g Newton. An alternative way to think of this is that it decides for you what computationally bounded observers are, and it restricts in gravity to semi-classical observers. Okay, so that's just a choice. We can do that. Now, this theorem that I showed you, it's on average, it's averaging over unitaries and states, but that's kind of unphysical because in reality, if you have some physical system, there will just be one Hamiltonian that describes the time evolution of that system. So we want this result to be extended to hold for fixed unitaries. And to do that, we can use some mathematical tools known as measure concentration to prove an extension to fixed unitaries and states instead of averaging over them. All right, and then finally, this non-simple observable Q that this theorem gives us, it really should survive what we call the large N limit, which translates to small G Newton. So we want that observable to actually exist in the semi-classical theory. Because ADS CFT is a statement at finite N, but we don't really know what the bulk looks like at finite N. We need that semi-classical limit to have some meaningful statement about event horizons or singularities. Okay, so what we do is we prove a corollary that this extension of this theorem also holds for infinite dimensional
Security
vector
parameters
spaces.
tell you sort of how hard it is to cut in computer language.
That's right. It's how hard it is to crack the code. Yeah.
And is it always on it? Or can you have exponential make a harder to crack code?
In situations where you care about computational security instead of statistical security, then you need a statement like this. So the question is, how well can polynomially bounded computers do in cracking this code?
Right.
And if you want to ask a question like that, you really need this thing to be polynomial. If it's exponential, it can be exponentially statistically secure, but that's sort of a meaningless statement if you want to ask about actual computers being able to do the job. Is that?
Yeah, so is the likelihood that this forms a dictionary to the equivalent statement in the black hole, is that just based on our computational competence, or is that, I mean,
Yeah, it's
why
based
is
on,
nature? I understand why we need polynomials, but why is nature?
it's because it restricts to the semi-classical limit of gravity. Yeah. So this is basically the distinction between being exponential in 1/g Newton, or well, doubly exponential in 1/2, or exponential in 1/g, which is the black hole entropy, for example, is that class of scaling. Okay, so I'm going to briefly go over this proof of this extension and the corollary, and then we'll see the theorem. Okay, so how do you extend this result to typical unitaries? As I said, we use some tools for measure concentration. So the idea is that you can bound fluctuations around the average fidelity. So for some typical unitary that's close to the average, bounded by epsilon close, then we can show that the probability that these fluctuations are bounded is very high. That this is 1 minus something that is going to be exponentially small as we take, especially as we take n to infinity. Now we prove this for higher random unitaries, but then using tools from cryptography, you can extend that to pseudo random unitaries. Reason being that if you couldn't, then you could use fidelity measurements to distinguish between random and pseudo random, but you're not allowed to be able to distinguish. So that's the idea of the proof. All right, so here's the theorem.
So, I have a question. When you said that the overlap is, you're not having sufficiently good overlap earlier, that means that you had this parameter that was order 1.
Yeah.
If it was order, say, 0.1, something like that, that's a 0.01. Is that, so all of this doesn't matter? It's just, rather what I'm asking, how small does it have to be for you to say that the overlap is good?
Yeah, I think it really needs to be order 1 because it's 1 minus some constant. And we want it to be closer to 0 than to 1.
Okay.
Kind of the interesting thing is that it does not scale with the dimension of the Hilbert space. It's really just a number that we know how to compute. I didn't write it because it's kind of some interesting
So
number.
it's really a bad overlap.
That's right. It's a number that we know that is order 1. Okay, so here's the theorem. So this is kind of simplified expression that I just wrote because it goes to zero as n goes to infinity. The actual expression is a bit more complicated because, for example, this dot, which is the average fidelity between the true time evolution and predicted time evolution, the predicted time evolution also depends on the true time evolution, because that's kind of the oracle that this algorithm was working with. So the actual expression is a bit more involved, but the statement is the same, that now consider some pseudo-random meter ensemble, some pseudo-random state ensemble. Now we have the security parameter that scales polynomial with n. Now any quantum algorithm that obeys some reasonable assumptions tries to learn the time evolution, produces U hat as its best guess, then tries to predict the time evolution of the physical state. Then with high probability, just read high here, then the overlap now for any typical unitary of the true time evolution and predicted time evolution is again bounded below 1 by this constant, this order 1 constant alpha, plus this epsilon, and this epsilon we can pick to be any number between 0 and 1, we pick it ourselves. So again, this overlap is really, really small. And then that implies that there exists some operator that can distinguish between the true and the predicted time evolution really well. Okay. Now, like I said, the final thing that we need is that this survives the large n limit. Now, the kind of technical difficulty here is that randomness and pseudo-randomness are not defined for infinite dimensional Hilbert spaces. So you need to make some reasonable assumptions on your states, which are defined as you take n to infinity. So we make that precise in the paper, but the upshot is that if you work through this in a good way, then you'll find that this distinguishing operator Q does really survive this infinite n limit. So it exists in the semi-classical limit. All right, so that was kind of the computer science part of it. Now let's talk about how we use this to prove cryptographic censorship. So the final thing we need is this statement that I said earlier, that the causal wedge is simple to reconstruct. So to connect that to the tools that we're using, the assumption that we need, which we think is well motivated, but we're not able to prove, is that there exists a low complexity quantum algorithm that I'll call a CW for causal wedge, that is that can reconstruct the causal wedge of any state in your code space. I'm going to motivate this assumption from 3 different routes. The first is from intuition, and we already talked about this. If your operator lies inside the causal wedge, then you could just send in some time-like observer. They could measure your bulk local operator and then come back up. That should be simple to do. Now, to make that into this formal assumption, what you further need is that there is some algorithm that can aggregate all of these local measurements into a prediction for the full time evolution of all of the operators in the causal wedge. But that seems reasonable. Now, the second motivation is from physics, that we actually know of a protocol that is able to do reconstruction on all operators in the causal wedge. It's called HPLL for the authors of that paper. So we know that we can do that in any causal region. Now, if there were some singularity here, we would still be able to do it here, and then do it in successive wedges. And then if there was some algorithm that could, again, aggregate all of these measurements, we would have this assumption proven.
Wait, sorry, what's the last feature? How you drawing causal wedge of time?
Yeah, so the singularity is technically not part of your spacetime. So you just end shortly before it. So you can do this in any of these causal wedges and then talk about that will give you the time evolution of all operators in the causally accessible region. And finally, from cryptography, that there actually exists such an algorithm that can predict time evolved expectation values of all simple operators. However, the assumptions.
Sorry.
Yeah, no, go for
So in the previous slide, typically the issue with like such exposed time singularities is that you have a Cauchy horizon. Therefore, if you take a early at a earlier time, if we take a space like hypersurface and set up some initial data, we can't predict what happens later, right?
Mhm.
And the argument that people technically give is we don't know what the singularity is doing.
Yeah.
So you need some boundary conditions on that.
That's right.
So even here, while the causal wedge doesn't contain the singularity, don't you need some sort of boundary condition on what the singularity is doing inside this causal wedge? Or-
That's why you need to do it at all of these successive wedges.
Okay.
So you just do it within a wedge, then you do it within the next. And then in all of these, there is some, as you said, there's some hypercircuits that you can use to just evolve back and forth within that, just within that wedge. So, all of these wedges are within the wedge, we have local hyperbolas. So you take some space-like surface here, you do back and forward time evolution to get everything there, then you move on to the next wedge. That's the idea.
And no signal from the naked singularity can enter these wedges.
The
Because
idea
it looks
is,
to me that it can.
well, within such a wedge, it cannot, right? Because it's gonna move out of this wedge. So within all of these wedges, you have global hyperbolas.
So I guess you're changing the definition of what we mean by the hypersurface. Space-like hypersurface is not ending at the singularity.
That's
In
right.
this case.
Well, the singularity is not part of your space now, so it cannot end there.
But in the classical, generally when we talk about it, when you draw these hypersurfaces.
Yeah.
The Cauchy horizon is there because your space-like hypersurfaces have an endpoint at the singularity.
No, but they cannot. Classically, they cannot. The singularity is not part of your space. Yeah. Right. And so here's a cartoon about computer science. Just kind of the extent of how I understand quantum machine learning. Okay. So on the basis of this assumption, then we have the following theorem. To consider the fundamental time evolution to be Newton, and then we're going to assume that is well approximated by a typical gravitationally pseudo-random unitary U, at least in some time band delta t. Now, if psi is some state whose complete time evolution has a geometric bulk dual, we need to input that because not all states in CFTs have actual good bulk duals. And then if after acting with U on that state, we got a typical pseudo-random state, then there must be a horizon in the space-time. I'm curious. Informally prove. By assumption, there exists a quantum algorithm ACW, which correctly predicts the expectation values of all causally accessible operators. Now, by theorem 1, hardness of learning typical pseudo-random unitaries, then for any computationally bounded algorithm, and so also for this algorithm, there exists some operator Q whose expectation value cannot be predicted. Since ACW cannot learn or predict this expectation value of Q, it must have support outside of the causal wedge, because ACW was able to do this for everything inside the causal wedge. Therefore, there has to be an event horizon. So here's the proof in a drawing. So if this time evolution is pseudo-random, sufficiently pseudo-random, such that now this state is also a pseudo-random state, then by our theorem of hardness of learning pseudo-random unitaries, there must be some Q that at least has support outside of the causal wedge. And that boundary between the causal wedge and the exterior of the causal wedge is the event horizon. Okay, so let's see. I'm going to skip this first part. Like a reasonable question that you might ask is are there even code subspaces that you could care about? Are there physical situations that you could care about that can host this gravitational amount of pseudo-randomness? Is this theorem even applicable in any reasonable setting? And we want to argue that yes, there are indeed interesting cases. I'm going to skip the first, but the second is going to be interesting for the case of cosmic censorship, which is a code subspace of states that you have some identical classical geometry plus fluctuations around it. And then we have the pseudo-random unitary dynamics in some order 1 time band on the boundary. So it's kind of like the picture that I showed on the previous slide. In such a code subspace, the geometry of states is going to always be preserved up to exponentially suppressed errors. So basically, it's a statement that if you have this time evolution, that will map your code subspace onto itself, which is important to apply this theorem. And then if we apply cryptographic censorship to such a code subspace, then we'll see that an event horizon must form. And the reason that we're going to care about a code subspace like this is that we think a potential example of such a setting is what we're going to call a large naked singularity. Okay, so let's bring singularities back into the game. So before we can kind of talk about severe enough singularities, we need to actually be able to classify or talk about the size of singularities. So this is kind of a difficult problem precisely because singularities are not part of the manifold. So we first need some tools to include it in our manifold. There is a way to do it. It's due to Dirac, that you can include the singularity as some set of points into your manifold.
Yes, sorry, when
Mhm.
you mean by, what do you specify size of the singularity, like the strength, how strong it is and it impacts, or like the,
Yeah, I'm going to, what, by size, I'm going to define a region on the boundary
okay,
that is the minimal region that you need to see the singularity.
Okay.
It's going to become clear in a bit.
yeah, thank
Mhm. So the way that we're going to define the size initially of some, possibly a subset of some singularity gamma. So again, the singularity now is a set of points that we have included in our space-time manifold. Then we're going to construct two sets of points on the conformal boundary, such that there are null geodesics, past or future directed, that go from the conformal boundary to that subset of the singularity. So here are some examples. So if we have both a non-empty P minus and a non-empty P plus, so again, these are the set. These are regions on the boundary, that there are points that you have past, or in this case, future directed null geodesics that reach this subset of the singularities. If you have both non-empty T minus and T plus, then we're going to say that the size of the singularity is the minimum of the two. Again, because that's the minimal time evolution we need to kind of see the singularity. In this case, they're equally large, but whatever, that could be different. Now, if one of them is empty and the other is non-empty, such as in the case of the evaporating black hole in ADS, then we're going to say that the size of the singularity is the size of the non-empty set. If both are zero, then we're going to say that the size of the singularity is zero. So again, the size is with respect to the boundary. Okay. Now, why is this a useful thing to define? It's useful from the point of view of naked singularities. So
So Adam, what does the size mean? If you have a space-like singularity? How do you,
yeah, so it's always going to be some space-time, the size. So this is some set of points on the boundary. And we're going to say that the size of the singularity is the space-time volume of this region near the boundary. And the reason that it's an interesting thing to define is that it's kind of the time band on the boundary that before you get here, you know nothing about the singularity. Now you enter this time band and you have some access to the singularity. That goes all the way on until here. And then after that, there's no point in time evolving further to learn new stuff about this.
so it's always finite.
Let's talk about that on the next slide.
Okay.
Yeah. Right. So the reason that we want to define it this way is because it has something meaningful to say about naked singularities. So here's our definition of three classes of singularities. Consider some incomplete spacetime with the singularity gamma scribe with respect to the conformal boundary scribe. And we're going to say that the size, we're going to assume that the size of the singularity, we've gone through this procedure on the previous slide, we're going to measure it in terms of the Planck length, or J Newton, to some power. We're going to say that it scales with the Planck length to some power. Then we're going to define it to be a classical singularity if this power is less than or equal to 0. The reason being that if it's bigger than 0, then as we take G Newton to 0 or the Planck length to 0, this is going to go away. So that's the other. So ideally, we would have separated this into two classes, classical and non-classical, the ones that go away in the G to 0 limit. However, we will see on the next slide that we need to divide the other category into two. If A is between 0 and D minus 1, sorry, D is the spatial dimensions. Then we're going to say that gamma is a semi-Planckian singularity. And if A is bigger or equal to D, we're going to say that it's Planckian. And the reason to distinguish between these two is that actually, it turns out that both these semi-Planckian ones and the classical singularities are large enough to accommodate gravitational pseudorandomness. Okay. So yeah, so they're basically finite, but they can go away in the semi-classical limit. Okay, so this is what I just said, that classical semi-Planckian singularities seem to be compatible with some code subspace that is sufficiently large that it can accommodate gravitational pseudorandomness. Okay, so here's quickly some examples. So here again is a time-like singularity. So this example is classical and it's naked. If we have the Horizon Nordstrom black hole in GS, then this singularity is classical, but it's not naked. And here is a point that I tried to make all the way in the beginning. If we look just at the endpoint of black hole evaporation, it's naked, but it's not classical. We expect that these sets go away as we take G to 0. Okay. So now let me try to substantiate this claim that classical and semi-Planckian singularities can accommodate gravitational pseudorandomness in their set of states. So the way that we want to think of time, we're interested in time-like naked singularities because those are the ones that are most disruptive for cosmic censorship. So we want to think of time-like naked singularities as imposing some kind of UV sensitive boundary condition. The reason is that the physics of this singularity is not accessible from an effective field theory point of view. However, we can have modes that probe the singularity, and we expect that they need to bounce off with some boundary condition that we fundamentally do not know because it's highly sensitive to the UV physics. But we still want to consider it as some sort of boundary condition. And the question is, can we define a code subspace that accommodates gravitational pseudorandomness from the EFT point of view? So are there enough effective field theory modes that can probe the singularity during this time window that we care about to host this amount of gravitational pseudorandomness? The question basically is a Hilbert space large enough to even have this amount of pseudorandomness? And so we can do a very simple mode counting to count the modes that from this boundary subset that can probe the singularity and get refracted off. And by the way, I didn't say that, but a reason that you might think that this incorporates pseudorandom time evolution in the boundary is that since we don't know what this boundary condition is, it's plausible that it's just going to spit out these modes with some random or pseudorandom phase. So that's kind of the intuitive picture of why this would imply pseudorandom time evolution. So you can do this mode counting and you'll find that the number of modes that can probe the singularity scales with Planck line in this particular way. You need to impose some constraints on this constant delta to make it physical, such that the sort of naive entropy of these modes does not exceed the Bekenstein bound. If you do that, then you'll see that for A in the class of classical or semi-Planckian that I defined on the previous slide, that this you can always pick a delta such that this number diverges to infinity, meaning that there's enough modes to host this gravitational amount of pseudorandomness. Okay, so what I want to say is that we've seen that these classical naked singularities are compatible with gravitational pseudorandomness. This I'd like to take as motivating the idea that the dynamics of strongly gravitating systems in the G to 0 limit may admit a description in terms of pseudorandom unitaries. If that is the case, then our theorem of cryptographic censorship guarantees that such spacetimes must also have horizon. And then we want to take this idea of cryptographic censorship together with the counterexamples that I gave in the beginning and the motivation from quantum gravity physics to put forth the following conjecture, the quantum cosmic censorship conjecture, that in quantum gravity, typical states with an emergent geometry do not have classical or semi-Planckian naked singularities. And this is the form of cosmic censorship that we think you should have in quantum gravity. Okay. I guess I'm done. Some remarks. So we proved that black holes are the exclusive source of pseudorandomness, because we've proved that if you have pseudorandom time evolution, then there needs to be a horizon. Therefore, if we do not have a horizon, there's no pseudorandomness. Okay. Now this is interesting because that actually suggests that spacetimes with naked singularities, were they to exist, are actually highly predictable. Contrary to sort of the intuition that we have that they're highly unpredictable.
Here you're assuming something about the naked singularities, right? That it does things in a random or to the random way.
I'm saying that if we do not have horizons, there is no gravitational pseudorandom that we've proven. That means that if naked singularities did exist, they could not have gravitational pseudorandom dynamics. And that suggests that they're actually predictable systems. So there's not this chaotic.
The question is, if I can come up with a classical geometry
Mhm.
with a timeline naked singularity, which is large area or whatever by your criterion. Are you saying that the
Well-
model is wrong, or are you saying,
No, but this is not classical.
I know, you're
Yeah.
saying that the moment you put quantum and take the limit G H bar go to 0, which to my mind says classical, but I'm giving you the classical.
Semi-classical.
Yeah, but you're saying that this classical, you won't even look at it because your theorem says it's wrong.
Sorry, what the model being?
A classical collapse model with a naked singularity.
No, that's fine. I'm just saying that it cannot be pseudorandom. The time evolution cannot be pseudorandom.
So you're saying it is predictable. It is naked, but it is not random.
That's right.
Predictable.
It's pretty.
Yeah.
I'm
Okay.
confused about this because you talked about event horizons, but you did not talk about Cauchy horizons, which time like naked singularities will. So how are you escaping the Cauchy horizon? Like, isn't it supposed to be all like, I would expect something to be related to killing horizons, not in particular event horizons and not Cauchy horizons. So I'm not entirely, I don't understand where Cauchy horizon don't matter.
Well, but the point is that if you don't have an event horizon, you could just go and probe the singularity and go back to the boundary. Okay, so I said that we want to say that typical states cannot have naked singularities in the absence of event horizons. So, what? Sorry, this is a bit confusing. So we've proven that if you start with some naked singularity that evolves in a pseudorandom way, then there needs to be an event horizon, but we didn't say how much of that singularity is actually, we couldn't prove that that singularity is also hidden by the event horizon. So typical states could still have naked singularities, but only in addition to horizons. And so the question that we did not answer, but that would be interesting to answer, is how much of the singularity can actually lie outside of the horizon. We already talked about this, but this cryptographic censorship theorem partially solves the teleology problem in the sense that we can actually diagnose event horizon information in finite boundary time. We don't need the entire history of the spacetime, which I think is kind of cool. And then another remark is that if we had a converse of cryptographic censorship, that could actually provide a definition of quantum event horizons, which is now lacking, as states undergoing gravitational pseudorandom time evolution with the semi-classical block dual in the large envelope. But we don't have this converse, but would be interesting to have. And then finally, I think kind of this open question is that are singularities in general, in fact, associated with large amount of pseudorandoms, such that we can really connect cryptographic censorship to cosmic censorship. All right. Let me end there.
Can you say a little bit more about what you mean by prediction when you say they are the naked singularities absent the pseudorandomness that requires a horizon are predictable? There's several sort of notions of predictability that I can think of. I mean, people often say if you had a naked singularity, then anything could fall in. So if you played it backwards in time, anything could come out. That's a certain kind of unpredictability, but I don't think that's the predictability that you have in mind. But
No,
gravity is
it's-
space-time, right?
I just mean the kind of GR formulation of asymptotic predictability.
Okay.
So, which is, if you look at the formal definition of weak cosmic censorship, it will have that in its formal definition
Okay.
as space-times evolving from smooth initial data that obey the dominant energy condition are asymptotic events. Yeah. And I think the intuitive notion of predictability is of unpredictability is chaos. That's the physical intuition of it. And so what we're saying is that if there is no horizon, then there's no gravitational pseudo-randomness, which is kind of this probe that we're using or proxy that we're using for chaos.
And is that equivalent to saying that the trajectory of a test particle in the nearby space-time over some decent amount of time tau is not, practically speaking, predictable?
If there were to be chaos?
If there was to be chaos?
That's right.
Mhm.
That's right. Yeah, or if you would have, it's basically the butterfly effect.
Yes.
And we're saying that you cannot have that if you. In ADS,
Yes.
So just to sharpen my understanding.
yeah, please.
Of what you're saying. So let me again go to a classical collapse model.
Mhm.
One that I have in mind, but the details don't matter. Spherically symmetric. So this guy collapses, it forms a naked singularity.
Mhm.
And then forms a horizon.
Okay.
So in the Penrose diagram, I got a horizon,
Mhm.
but there's a piece of naked singularity sticking out.
Yeah.
Which can communicate with future infinity.
That's right.
Okay?
Mhm.
It has a horizon. So
Yes.
what would you say about this guy?
Totally allowed.
This is
We
allowed.
cannot rule it out. Yeah.
You cannot rule it out,
Cannot
and this
rule it
guy will be unpredictable?
No.
Okay, so you're saying that the naked singularity will still be completely predictable in this case?
Sorry, no, this can be unpredictable. Yes.
This can be
Yeah,
unpredictable.
because there is a horizon.
Okay, even though the singularity is actually sticking out of the horizon.
That's
that
right, because
doesn't
that's
matter.
exactly actually, that's the only thing that we could say, that singularities must exist. Sorry, that naked singularities. If there is naked singularities, then there also need to be horizons.
Good.
Yeah.
But this is not cosmic censorship, because.
It's not cosmic
this
censorship,
guy that's
that's right.
sticking out is
That's right.
violating.
Absolutely, no, so we're working towards the goal.
Okay,
Perfect
okay.
one, yeah, no, absolutely. Yeah.
Whereas if I just have an isolated naked singularity, no horizons at all, you would say this guy is not random. This is
That's right.
completely predictable.
That's right. That's the point.
So it's not really a singularity worth its name.
Yeah.
Okay.
Yeah, so, but I think that's interesting, right? Because we do tend to think of, even if you have a completely naked singularity, you would say that's probably a highly unpredictable spacetime.
Yeah.
So whatever might happen. And we're saying that seems to not be the case. Which is very counterintuitive. Yeah.
The question timing that was Primus's findings.
Yeah.
Plans based on the timeline it is incorrectly.
Sure.
So is that sort of related to something about?
Yeah.
Not sure.
I mean, we don't have, at this point, we cannot say anything about fast space. I don't think it's a moral barrier, but it's definitely a technical barrier, because all of this cryptography really relies on working in the non-gravitational description.
Right.
Now, I do believe that there is some fundamental quantum gravity description, some fundamental description of quantum gravity in flat space. That then in the if you would have the pseudo-random time evolution in the fundamental description, I think you would be able to say something meaningful about singularities in flat space. I'm working on something related now in the sitter, where we know that there's also horizons. Sorry, this is not going to answer your question, just also something that's interesting. But in the sitter, that we know that time evolution is not actually unitary. So we cannot use this notion of cryptographic censorship, which really relies on unitary time evolution. However, I believe that on the cryptography side, there is a way to extend these results from unitaries to general time evolutions. Just to say that you have some pseudo-random time evolution that is not a unitary. If that works out, then it's very interesting to kind of have maybe a cryptographic formulation of the de Sitter cosmological horizon, or the cosmological horizon in our universe, which we know is highly observer dependent, contrary to the black hole horizon. And the question is actually kind of, is the relaxation from unitary time evolution to non-unitary time evolution, is that what gives you this observer dependence? That would be, I think, very interesting. But so I do think there is extent that you can use these cryptographic tools to say something about fast space and de Sitter. But it needs a bit more work on the cryptography side, and I am not so well versed in cryptography to make fast progress on that. But maybe some.
We should probably end here.
Yeah.
But we can continue using this one to discuss.
This people say stuff.
Thanks again.
Great.
Yeah, thanks a lot. Thanks for coming.
Hey, thanks, Evita.
Hey.
I got you on Zoom and then like.
Oh, nice.
So,
While we have the space.
so what about null naked singularities? Do you think, I didn't
Oh.
think abstraction to null naked singularities, because
Oh,
from them directly collapse just without, right? There are solutions.
yeah, absolutely. There is no obstruction.